Hey everyone, welcome back. Today we're going to be talking about section 2.2 in the book. That's on graphs of functions. So, to graph a function, we graph on a coordinate plane. All the points x comma f of x, where x is in A, or sorry, I shouldn't use that. X is in A, which is the domain. So all the legal x's that you could plug in, you plug it in and get a point f of x back, or the point is x comma f of x, and then you just graph all of those points and you'll have the graph of the function. But obviously it's not possible to individually graph like every real number, so that's why we have our techniques that we're going to learn in this section. So I guess in other words of saying, the graph of f is a set of all points. So using our set notation, we just have a set of all the x comma f of x such that x is in the domain. Alright, so we have a couple common types of functions, and I'm going to list them, and then at the end we're going to actually have like a little, well, the book has a table that has like common pictures of all these types of graphs. So a linear function is something that looks like f of x equals mx plus b, like we were talking about last time with the lines. That's just a standard equation for a line. And then you could have a constant function. That would be like if you had f of x equals just a constant b. And remember, that would represent a horizontal line. And then you could have the power or root function. The power one being if you had like f of x equals x to the nth power. The root one if you had f of x equals nth root of x. So these are all common types of functions. This is not the complete list of functions, but this is all we're going to be working with because they're just the ones that are like basically defined using like the most simple algebraic operations. All right, so okay, so the first way that we learned how to graph functions, well, we didn't call them functions back in chapter 1, but we did learn how to graph expressions by plotting points. So this is the most simple way to do it, but also the most like you need the least amount of like background knowledge to be able to graph a function like this, but it's the most difficult way to do because it takes the most amount of time. So like this, we would just be like plugging in x's, but remember you have to plug in x's that are in the domain, and we know that the domain of this is all x is greater than or equal to 0. So we can't have a negative x plugged into the square root. So our graph won't include any of those x values. So start with 0. F of x would be square root 0 would be 0. And then 1, square root of 1 is just 1. If we had 2, f of x would be square root of 2, which is irrational, so we just leave it like that. 3, square root of 3, same thing. 4, square root of 4 is 2. And so on. We could do this forever, but we're not going to because it's going to take too long. Alright, so now the graph, we just plot the points. So 0, 0, and then 1, 1. And then root 2 is somewhere around 1.4. And root 3, I believe, is somewhere around 1.7 to 1.8, somewhere around there. But so you get 1, 1, and then 2, and then like 1.4 or something, and then 3. And so we see that the graph is kind of flattening out. 4, 2, so if we drew a curve through it, it looks something like that. And that is roughly what the square root function looks like. So yeah, this is not the best way to graph functions, but it is a way, like a fail-safe way, that will always work. All right, so we talked about piecewise functions a little bit last time, but not about graphing them. So remember, piecewise function would be something that looks like this here. We'll just jump right into an example. So you have like f of x equaling two different things depending on what x you plug in. So we're going to say f of x equals 3 if x is less than 0, and f of x equals x squared if x is greater than or equal to 0. So make this a little straighter. All right, so we have to write or draw the graph of the function for each of the different intervals we're given. So the first one, if x is less than 0, so if we have any x's like over here, but not including 0, then it's just, the value is just 3. So it's 3 all the way up until 0, which we have an open circle at. And then, and so this is like going out forever that way. And then f of x equals x squared if x is greater than or equal to 0. So when x equals 0, it equals x squared, which is 0 squared, which is 0. So our first point of the new piece is the point 0, 0. And then the rest of it, if we just remember our graph of f of x equals x squared looks like this, then we have this right piece is the piece we want, because that's for all the x's greater than or equal to 0. So that would be the rest of the graph. So this is what the graph of f of x looks like. It's just two pieces where each of the individual pieces are like if you had the whole function, like f of x equals 3 for all of x's, but you just cut off the part where it's not defined that way for us. All right, and then another example, this one is important because sometimes absolute values can be pretty confusing. So just to explicitly say what we mean by an absolute value, so let's say we have f of x equals absolute value of x minus 1. That is a function, and it is actually a piecewise defined function because it's two different functions on two different intervals. So if we remember what like absolute value x, that is x if x is less than, or sorry, not less than, it's x if x is greater than or equal to 0, it's minus x if x is less than 0. And so we use the same thing here. The absolute value of x minus 1 is just the same thing, x minus 1, if what's on the inside is greater than or equal to 0. And it's the opposite if what's on the inside is less than 0. So now we can rewrite what we mean by this. So it's x minus 1 if x is, and rearranging that inequality, x is greater than or equal to 1. And it's 1 minus x if x is less than 1. And so now we can draw this. So if we have x greater than or equal to 1, then we have, so let's just draw these two functions, x minus 1, and 1 minus x. Let's just graph the whole thing, but with like dotted lines. So x minus 1 has a slope of 1 and y-intercept -1, so it goes through -1 and looks like that. And then 1 minus x has a slope of -1 and a y-intercept of 1, so it's going to look something like this. And then I didn't draw it perfectly, but these two lines intersect right there at the point 1, 0. So these are the two graphs of x minus 1 and 1 minus x for like the whole real number domain, but we only want the x minus 1, which is the positive sloped line, for x bigger than or equal to 1. So it looks like this is what we want. For x bigger than or equal to 1, we want that line. And then the other negative sloped line is for all the x's less than 1. And so we get that piece. And so that is the graph of the function f of x equals absolute value x minus 1. Just a little cleaner version, it would look something like this. And then you can kind of tell that that's just like the regular absolute value graph, which looks like that. It's just moved over to the right. All right, and then one last function that they talk about in the book is f of x equals, this is called the, I think it's called the greatest integer function, the nearest integer function. I always just call it the round up, or like the ceiling function. So whatever x is, like let's say x was 1.8, what f does is it rounds it up to the nearest integer. So like if we were at -1.5, the next highest integer would be -1, right? Because we're on the number line, like 0, -1, -2. If we're like somewhere right there where 1.5 is, we always are going up, meaning to the right. So that's why 1.5 goes to -1.5 goes to -1, but like positive 1.5. So if we had that, that would go to 2. So that's just the like round up function. So the graph of that would look like this. So at 0, what do we do at 0? Okay, so I guess if we're at an integer like 1, yeah, then 1 gets sent to 2 because it's that's just, I guess that's just how we define it. So 0 like x equals 0 gets sent to 1, and then everything gets sent to 1, just so we can see what we're dealing with. So 0 gets sent to 1, and everything gets sent to 1 except for all the way up to 1, which then gets sent to 2. Sorry, so 1 gets sent to 2, everything gets sent to 2 up until 2, which gets sent to 3. And we start getting what looks like this like staircase, and we can do it backwards too, so like that, and then it just goes on and on in each direction. Alright, so that's just a couple of piecewise defined functions. And then we have another quick little definition. A function is called continuous if it has no breaks in its graph. So looking back at the functions we just talked about, this first one is not continuous because it has a break where at x equals 0 you make a big jump. This one doesn't have that jump, even though it has like a little sharp point. It never actually like has a break in the graph. And then obviously this one also has a break. This one has like infinite amount of breaks because like every integer you go up, it'll have another break. So this first one is just not continuous at one point, where this function is not continuous at many points. All right, so the vertical line test is a test to see if a graph represents a function. So first, I want to recall that a function assigns to each x in A the domain. The domain of F. So it assigns to each x in the domain exactly one, which is important, element f of x in B, which is, remember, the set that f of x lands in. This, yeah, so it's mostly going to be, is almost always going to be the set of real numbers, because our functions are always real valued functions. So all right, so since we know that a function assigns only one value to each input, so I guess another way to state this is we cannot have f of x equaling two different things. Because then that just breaks the definition of the function, which in the definition it says that it has to assign only one thing to each input. So if we had f of x equaling two different things, like let's say we were doing the graph of f of x equals x, so but then like if we had like f of 1 equals 1 or 2. We'll just say like that's our rule. F of x equals x except for at 1 when it equals 1 or 2. So then it would look like this. We have 2 points above x equals 1 because it could equal both of them. And then it's like how do we draw this graph? Because this point is directly above it. So like if we do that, this isn't a valid graph, and that's because we assigned 2 points to the point, or we assigned 2 values to the input x equals 1, and so that's what we're getting to is that if the graph doesn't satisfy the vertical line test, meaning you should be able to take a vertical line and just run it through like to the right scanning and never have 2 points on that line and on the graph. So we can see right here that there are 2 points vertically on top of each other, so this graph does not represent a function. All right, so one thing we could have is just the function f of x equals x. And kind of what I was alluding to before is that this does pass the vertical line test. If you take a vertical line and pass it through any part of the graph, you will not have more than 1 point intersect. So this one passes. But then, so I shouldn't have written it like this. I should have written it like y equals x. Because when we say f of x, that's implying that we're dealing with a function, so it better pass the vertical line test. Otherwise, we're misinforming whoever's reading our work by writing f of x because it's not a function. But in this case, it is, so we could have written f of x equals x. But in this example, one thing that's not a function is if we had x squared plus y squared equals 1, the circle of radius 1. This is not a function because over here it looks good. It's passing the vertical line test right here. All right, looks like we only got 1 point, so we're good. But then right here, there's 2 points on the same vertical line, so this graph is not a function. And then this last part of section 2.2 is going to explain why a circle is not a function. So one question you might ask is, when do certain equations represent functions? Like if we were just given x squared plus y squared equals 1, and like without our knowledge from the last chapter, we just didn't know that was a circle. And then we're asked, all right, is this a function? How are we going to be able to figure that out? So what we do is we solve the equation in terms of y, and then ask, do we only get one output per input? So one example, let's say we had this equation, y minus x squared equals 0. So what we do, we solve for y, we get y equals x squared, And then we ask ourselves, all right, if we plug in a certain x value, are we going to get one or more than one solution? So, I mean, this particular equation we already know does represent a function. Its graph looks like this. And definitely if you plug in any x, you just get back its square, which is a unique number. So this one definitely passes as a function. But what if we had this equation, y squared minus x squared equals 0? So we solve for y, get y squared equals x squared, and we need y by itself, so we take the square root. But when we take the square root of a variable, then we need to account for that. It could have been the positive or negative version. So we get y equals plus or minus x. So if we plugged in like x equals 1, we would get y equals plus or minus 1, which is two different answers. So this is not a function. And actually, its graph looks like this. So y equals plus or minus x. So for the whole real number line, we could have y equaling x, which is this line, or y equaling minus x, which is this line. So this is actually the graph of this function. So clearly it does not pass the vertical line test either. So yeah, this is not a function. But yeah, we explicitly showed that by solving for y and being able to tell that it definitely has two distinct solutions for every x value except for x equals 0, in which case it has 1. But it doesn't matter because that as long as it doesn't pass the vertical line test just 1 point, then it's not a function. And then so this is a section that's included in the book, and I urge you guys to look at it. It's a table with examples of graphs of things like f of x equals mx plus b, so like a linear equation, like the power function, a root function. It has examples of the reciprocal of the power function, which is very important, like absolute value equation, and also the ceiling function. So yeah, those are. It's nice to have that table that's in the book handy so that you can just kind of take a shortcut and be able to know like what the graph generally looks like, and then work from there. All right, so that finishes up section 2.2. And here are the homework problems. All right, so I have office hours again tomorrow from 1 to 2, and just reach out to me if you have any questions. Have a good day.